The dawn of the universe, light, atoms, and the first stars before the first tick of time, before the cosmos had stretched even an inch across the void, there was only potential. A singularity, infinitely dense and unimaginably hot, held within it the seeds of everything that would ever exist. Imagine a point smaller than anything the human mind can truly comprehend, yet containing the energy for billions of galaxies, for suns and planets, for life itself. And then, in a moment beyond perception, this point erupted. A burst of primordial light tore through the darkness, scattering photons in all directions, illuminating the nascent universe for the first time. But this light was not just illumination, it was the very foundation of matter. It was the energy that would give rise to the first elementary particles, quarks, electrons, neutrinos. These building blocks, appearing in an almost chaotic dance, would become the architects of atoms, molecules, and eventually, the intricate structures of stars and planets. The first quarks combined in intimate unions to form protons and neutrons. Electrons, charged and restless, orbited these nascent nuclei. The universe, though still infantile, was learning the rhythm of creation. From this delicate choreography emerged hydrogen and helium, the simplest and earliest atoms. These primordial gases, though sparse, carried within them the potential for everything that would follow. As atoms coalesced, space itself began to take shape. Not merely an emptiness, but a dynamic, expanding canvas, stretching faster than the mind could track. Galaxies, invisible at first, began to form, gathering matter under the subtle tug of gravity. This gravity, one of the fundamental forces that had quietly emerged from the chaos, began to sculpt the universe, drawing hydrogen clouds into spiraling formations that would ignite as stars. And then, like a cosmic symphony reaching its first crescendo, the very first stars ignited. Nuclear fusion within their cores transformed hydrogen into helium, releasing tremendous amounts of energy, casting the first persistent light into the expanding void. These stars were not solitary, they were the harbingers of galaxies, the furnaces in which heavier elements would be forged. Carbon, oxygen, and iron elements essential for planets, oceans, and life would owe their origin to these first stellar beacons. Every photon that traveled, every particle that collided, contributed to an unfolding narrative of order from chaos. The universe was no longer an abstract concept. It was a living, evolving stage, preparing for the complex structures to come. Nebulae coalesced, cosmic dust gathered, and the first whispers of galaxies became visible against the dark canvas of space. Even as the universe expanded, subtle forces ensured that matter did not merely drift aimlessly. Gravity, electromagnetism, and the yet mysterious dark matter guided the arrangement of cosmic structures. Stars formed clusters, clusters became galaxies, and in this intricate dance, the stage was being set for solar systems and eventually, planets like Earth. This was a universe in its infancy, but every process, every reaction, laid the foundation for the future. From the searing brilliance of the first light to the birth of atoms and the ignition of the first stars, the story of creation was unfolding, a story that would eventually lead to planets' oceans and the first sparks of life. The cosmic tapestry was being woven, thread by thread, particle by particle, light by light. The dawn of the universe was not a simple explosion, it was a complex, awe-inspiring emergence of order, energy, and potential. Each moment, each interaction contributed to the grand narrative that continues to unfold to this very day, billions of years later in galaxies far beyond our own. The universe, still in its infancy, was no longer just a canvas of light and scattered atoms. It was a stage governed by invisible hands, the fundamental laws of nature. Gravity, the force that tugged matter together, began its meticulous orchestration, shaping clouds of hydrogen and helium into massive stellar nurseries. Electromagnetism guided the behavior of charged particles, while the strong and weak nuclear forces determined the very structure of atoms themselves. Without these laws, without this precise cosmic choreography, matter would remain formless, energy chaotic, and the universe a dark void without pattern or meaning. As the first clusters of atoms assembled into the earliest stars, another unseen player began its work: dark matter. Invisible, mysterious, and enigmatic, it did not shine or scatter light. Yet its gravitational influence held the early cosmos together. Galaxies, fragile at first, relied on this hidden scaffolding to form spiraling arms and dense cores. Imagine billions of stars weaving themselves into clusters, each movement dictated by forces that had existed since the universe's inception, yet only now revealing their full influence. And then there was dark energy, a pervasive, accelerating force pushing the universe apart, even as gravity pulled it together. The expansion of space was no longer a simple aftermath of the Big Bang. It was now an intricate dance between creation and dispersal, contraction and acceleration, tension and balance. Scientists today still grapple with its mystery, but in these earliest epochs, dark energy quietly shaped the destiny of galaxies, dictating the speed at which cosmic structures separated from one another. Meanwhile, within this evolving cosmos, the first stars aged and died in spectacular supernovae. These colossal explosions were not mere fireworks, they were forges in which heavier elements were created, scattering carbon, oxygen, nitrogen, and iron across the universe. These elements, once forged in the heart of a dying star, would seed future generations of stars, planets, and ultimately life itself. Without these stellar deaths, planets like Earth and the chemistry of life could not exist. Galaxies began to organize themselves into clusters, superclusters, and vast cosmic filaments spanning millions of light years. Spiral arms, elliptical cores, and halo structures formed naturally, a direct consequence of gravity interacting with dark matter and the residual energy from the Big Bang. It is breathtaking to imagine that the patterns we observe in the night sky today, galaxies, clusters, and superclusters, are echoes of processes that began billions of years ago, guided by the fundamental forces we are only beginning to understand. At the same time, some cosmological theories explore the possibility of multiverses, parallel realities born from the same primordial conditions. Could other universes exist alongside ours, each with its own laws of physics, its own stars, and its own fate? These ideas border on philosophical speculation, yet they expand our understanding of what it means for something to exist, to be created, and to unfold in time and space. Religious perspectives, too, provide profound reflections on these mysteries. Many traditions describe the cosmos as a carefully ordered creation, governed by divine wisdom. The heavens, the laws of nature, the unfolding of light into matter—all these can be seen as expressions of an intricate, purposeful design, a reminder that the universe is not merely a collection of atoms, but a theater of astonishing complexity and meaning. In the midst of all this, the first stars gave birth to their own planetary systems. Nebulae condensed under gravity, forming disks of dust and gas, where the earliest planets began to coalesce. These young worlds were harsh and volatile, yet within them lay the potential for chemistry, oceans, and eventually, life. The universe, though vast and seemingly indifferent, had begun the delicate process of preparation for the emergence of complexity, life, and consciousness. Every photon, every atom, every gravitational interaction was part of a vast cosmic narrative. From the invisible scaffolding of dark matter to the fiery deaths of the first stars, the universe revealed itself as a finely tuned mechanism, balancing expansion and contraction, creation and transformation, chaos and order. For the first time, the cosmos was more than light and particles, it was structure, law and purpose unfolding on the grandest imaginable scale. The dawn of galaxies was not just a spectacle. It was the foundation of cosmic architecture. From these first galaxies, the seeds of everything that would follow solar systems, planets, oceans, and life were planted. The universe had moved from randomness to rhythm, from chaos to a magnificent ordered complexity, stretching endlessly into the unknown. In the vastness of the early universe, as galaxies began to take shape, the life cycles of stars dictated the next phase of cosmic evolution. Stars, born from immense clouds of hydrogen and helium, shone brilliantly, yet their existence was always temporary. In their cores, nuclear fusion transformed hydrogen into helium, releasing incredible amounts of energy, sustaining light and warmth across billions of light years. But when the fuel was exhausted, the universe witnessed some of its most spectacular phenomena: the birth of black holes and the cataclysmic death of massive stars and supernovae. Black holes are not mere voids. They are the remnants of stars that collapsed under their own gravity, compressing mass into a point of infinite density. Imagine a star many times the mass of our Sun shrinking into a single unfathomable point. Its gravitational pull is so intense that not even light can escape. These enigmatic objects became anchors in the universe, shaping the movement of galaxies, affecting nearby stars, and even warping the fabric of space-time itself. Supernova, on the other hand, were explosive finales that scattered heavy elements across the cosmos. Carbon, oxygen, silicon, and iron elements crucial for planets, oceans, and life were forged in the heart of dying stars. Each supernova sent shockwaves through surrounding clouds, triggering new waves of star formation. The universe, though violent and unforgiving, was simultaneously creative, recycling matter, and seeding the next generation of stars and planetary systems. In these early cosmic epochs, galaxies were no longer mere clusters of stars. They were intricate ecosystems bound by gravity and dark matter, interacting with one another, merging, colliding, and evolving. The Milky Way, in its infancy, was already forming through such interactions, a young spiral slowly gathering mass and preparing to host its own solar system billions of years later. Imagine for a moment the scale of this universe, billions of stars lighting the darkness, each with its own story of birth, life, and death. Black holes lurking invisibly holding galaxies together. Supernova exploding with unimaginable energy scattering the building blocks of future worlds. It is a universe that is both orderly and chaotic, beautiful and terrifying, governed by forces that have persisted since time itself began. But the story of the cosmos is not purely physical. Philosophers, theologians, and scientists have long pondered the purpose behind these processes. In many religious traditions, the birth and death of stars are seen as signs of divine order, demonstrating wisdom and balance in the cosmos. The stars are not merely luminous spheres of plasma. They are beacons of a greater design, milestones in the unfolding narrative of creation. Meanwhile, the universe continued to expand. Dark energy accelerated this growth, ensuring that galaxies drifted apart even as gravity bound their internal structures. In the interplay of these cosmic forces, stars and galaxies matured, forming stable systems capable of supporting planets. Nebulae enriched with heavy elements from dying stars became fertile grounds where new stars and planets would emerge, setting the stage for the eventual birth of Earth-like worlds. The early universe was a dynamic laboratory. Each event, fusion, collapse, explosion, was a lesson in cosmic chemistry and physics. The atoms formed in the cores of stars would one day become water, rocks, and organic molecules. They would travel across space, riding on light-years-long journeys, and accumulate in nascent planetary systems. This was the universe preparing for life, for consciousness, and for the complex interplay of matter and energy that would make existence as we know it possible. As we observe this era through the lens of astronomy, physics, and cosmology, it is easy to marvel at the sheer scale and complexity of these processes. The birth of black holes, the explosion of supernova, and the formation of galaxies are not isolated events. They are chapters in a continuous story that has been unfolding for billions of years, a story that connects every atom in your body to the stars above. The universe, in this phase, was no longer a chaotic cloud of particles. It had become a structured, evolving cosmos, with stars and galaxies following patterns dictated by fundamental laws. Every gravitational pull, every burst of energy, every collision of cosmic bodies contributed to an intricate web of matter and energy, laying the groundwork for planetary systems, oceans, and ultimately, life itself. Billions of years had passed since the first stars ignited, and the universe, once a formless expanse of energy and particles, had now organized itself into intricate structures of matter and light. Among these structures, a particular region of the Milky Way was beginning to undergo a transformation that would ultimately give rise to our solar system. A massive cloud of gas and dust, a stellar nursery enriched with elements from countless generations of stars, started to collapse under its own gravity. This cloud, known as the solar nebula, was destined to become the cradle of our Sun and its accompanying planets. Within the nebula, gravity caused denser regions to condense further, forming a rotating disk. At its center, pressure and heat increased until nuclear fusion ignited, giving birth to our Sun. Imagine this newborn star, a furnace of unimaginable energy, radiating light and warmth across the swirling disk of dust. Around it, particles collided and stuck together, forming planetesimal small rocky and icy bodies that would eventually merge into full-fledged planets. The young solar system was a violent place. Collisions between forming planets were frequent, releasing immense amounts of energy and reshaping the nascent worlds. One of the most dramatic events was the impact between Earth and a Mars-sized body. Theorized to be Theia, this colossal collision ejected vast amounts of debris, which eventually coalesced to form the Moon. This cataclysmic event not only shaped Earth's satellite but also influenced the planet's tilt, rotation, and climate factors crucial for the development of life millions of years later. Meanwhile, the inner planets, including Mercury, Venus, Earth, and Mars, became predominantly rocky, while the outer planets, such as Jupiter and Saturn, accumulated massive gaseous envelopes. Asteroid belts formed, retaining remnants of the early solar system, frozen in time. These early formations were not random. They were governed by the same laws of gravity, motion, and energy that had orchestrated the cosmos since the Big Bang. On Earth, volcanic activity dominated the landscape. Magma flowed freely, shaping mountains, valleys, and the primordial crust. The atmosphere, initially thin and filled with toxic gases, gradually transformed. Water vapor released from volcanic outgassing began to condense, forming the first oceans. These vast bodies of liquid water became the cradle for chemical reactions, setting the stage for the origin of life. The early Earth experienced constant bombardment from comets and asteroids, delivering not only heat and energy but also essential elements such as carbon, nitrogen, and water. Each impact reshaped the planet's surface, creating new landforms and influencing the chemistry of the oceans. It is within this turbulent, yet fertile environment that the building blocks of life, the first amino acids, nucleotides, and organic molecules began to assemble. Temperature fluctuations, volcanic activity, and chemical reactions in the oceans created a dynamic laboratory. Lightning storms, ultraviolet radiation, and geothermal energy catalyzed reactions that may have led to the first primitive life forms. Imagine a single-celled organism, microscopic yet brimming with potential, surviving in the hostile oceans of early Earth. This tiny entity marked the beginning of life, a bridge between chemistry and biology, between the inanimate and the animate. Meanwhile, the sun's radiation drove the early climate, creating weather patterns and ocean currents that helped distribute chemical compounds across the planet. Plate tectonics slowly began to reshape continents, forming the first stable landmasses. Mountains rose and eroded, rivers carved valleys, and the stage was set for an environment capable of supporting increasingly complex life forms. As we observe this era through the lens of modern science, it becomes clear that the formation of the solar system and early Earth was not mere chance. It was a symphony of forces: gravity, collision, chemical reaction, and energy transfer that orchestrated the creation of a planet capable of harboring life. The elements forged in ancient stars, scattered across the cosmos by supernova, had finally found their way into Earth's crust, oceans, and atmosphere, creating the chemical foundation for biology. The cosmos, vast and ever-expanding, had now delivered a world ready for life, a planet teeming with potential, prepared by billions of years of cosmic evolution. The stage was set for the first sparks of biology, for the first signs of consciousness, and for the intricate dance of matter and energy that would ultimately give rise to every living being that would ever walk upon this planet. Imagine a world bathed in a pale sun, its oceans shimmering under the first light, yet still untouched by any creature. This was the Earth of over 4 billion years ago, a planet in transition, where chemistry and geology conspired to give birth to life itself. In the swirling oceans, molecules of carbon, hydrogen, oxygen, and nitrogen, the very elements forged in ancient stars, collided and combined, creating complex organic compounds. These compounds, carried by currents and heated by volcanic vents, began to assemble into structures capable of replication. Photosynthesis, one of the most important biological innovations in history, emerged from these early organisms. Tiny bacteria began to harness the sun's energy, converting light into chemical fuel, releasing oxygen as a byproduct. This oxygen gradually accumulated in the oceans and, later, in the atmosphere, creating a breathable environment for future life forms. This great oxidation event was not merely a chemical change. It was a transformation that made complex life possible. The Earth's surface, still volatile and shifting, provided both challenges and opportunities. Volcanic islands rose and sank, tectonic plates collided, and continents slowly drifted apart. Life adapted to these changes, finding niches in deep-sea hydrothermal vents, shallow coastal pools, and later, terrestrial environments. Each adaptation, each genetic innovation, pushed life toward greater complexity. During this epoch, genetic material DNA and RNA emerged as the blueprint of life. These molecules encoded information, allowing organisms to pass traits from one generation to the next. Mutations introduced variability, and natural selection acted as a sculptor, shaping life into ever more efficient forms. It is here, in the deep and quiet oceans, that evolution began its slow, inexorable work, crafting the diversity of life we see today. Consider the first multicellular organisms. Simple colonies of cells began to specialize, dividing labor and creating the first rudimentary tissues. These developments paved the way for organisms capable of innovation. Soft-bodied organisms with primitive nerve networks started to sense their surroundings, responding to light, chemical gradients, and physical touch. This new ability to perceive the environment marked a crucial turning point, allowing organisms to move, to hunt, and to avoid being hunted. Small, undulating creatures navigated through shallow waters, their movements slow yet deliberate as the first food webs began to form. Around 600 million years ago, the stage was set for the Cambrian explosion, a period of rapid evolutionary innovation. During this remarkable epoch, life diversified at an unprecedented rate. Skeletons, shells, and other structural adaptations appeared, leaving behind the first traces of what would become the fossil record. Trilobites, sponges, and early arthropods populated the seas, each organism a unique solution to survival, showcasing nature's limitless inventiveness. Meanwhile, photosynthetic organisms continued to pump oxygen into the atmosphere, gradually altering the chemical composition of both air and water. Oxygen, once a rare and dangerous molecule, became essential, enabling more complex metabolisms and the development of larger, energy-demanding organisms. Life was no longer confined to microscopic forms. The oceans teemed with diversity, a primordial symphony of movement, interaction, and adaptation. Predation introduced new evolutionary pressures. Organisms developed hard shells, spines, and defensive mechanisms, sparking an arms race that accelerated the pace of change. Cooperation and symbiosis also emerged, with different species forming mutually beneficial relationships. Simple ecological networks became increasingly intricate, laying the foundation for the first true ecosystems. Their presence stabilized sediments, created oxygen-rich zones, and provided the scaffolding for future terrestrial colonization. The interplay between organisms and their environment was now a dynamic feedback loop, shaping both biological forms and planetary conditions. Predators, scavengers, and grazers moved through the water, creating early food chains and driving energy flow through these nascent ecosystems. The arrival of plants on land was more than a botanical curiosity. It fundamentally altered Earth's atmosphere and soils. Photosynthesis now occurred not just in the oceans but across continents. pumping oxygen into the air and drawing carbon dioxide from it. Soil formation began as roots penetrated rock, breaking it down and mixing it with organic matter. This process set the stage for ecosystems that could support animals, insects, and eventually humans millions of years later. Life on land required new adaptations. Early arthropods, spiders, millipedes, and insects crawled onto these nascent green landscapes, exploiting untapped food sources. They were the first terrestrial animals perfectly adapted to the microhabitats created by pioneering plants. Simple exoskeletons prevented dehydration, while segmented bodies allowed movement over uneven terrain. Predators followed, and food webs moved from ocean to shore as life began to colonize every available ecological niche. Rivers and wetlands acted as corridors for expansion, allowing some aquatic organisms to make the leap to land. Lungs and limb-like appendages evolved over millions of years, enabling early amphibians to exploit both aquatic and terrestrial environments. Imagine the first creatures to crawl from water to land, slowly discovering a world filled with light, oxygen, and new possibilities, yet fraught with challenges from predators to the harshness of the sun. The Carboniferous period, nearly 360 million years ago, marked a pinnacle of terrestrial development. Vast forests of ferns, club mosses, and horsetails created towering green landscapes, shading the ground and creating humid microclimates. These lush environments supported enormous insects and other invertebrates, some the size of modern birds, illustrating the creative power of evolution under the right conditions. As plants spread, so did animals that relied on them. Herbivory emerged as a driving force of evolution, with insects and early vertebrates adapting to new diets. Ecosystems became increasingly complex, with predator-prey dynamics, competition, and symbiosis all shaping the evolutionary trajectory of terrestrial life. Life on land was no longer a fragile extension of the oceans, it had become a thriving, self-sustaining biosphere. These early terrestrial habitats also influenced the global climate. Forests absorbed carbon dioxide, regulated humidity, and contributed to the formation of rich soils. Seasonal cycles became pronounced, rivers carved valleys, and the interplay of geology and biology created dynamic landscapes that would define Earth for millions of years. By the end of this era, the Earth had transformed into a planet of vibrant land ecosystems. From tiny mosses clinging to rock to sprawling forests harboring enormous insects, life had established a foothold on continents, ready for further evolutionary leaps. Every adaptation from roots to lungs exemplified the relentless ingenuity of life responding to new challenges and opportunities. Imagine walking through a primeval forest, millions of years ago, where the air is thick with the scent of lush plants, and the ground trembles under the steps of creatures unlike anything we know today. The Earth had become a stage for vertebrate organisms with backbones that had conquered land and evolved into extraordinary forms. From early amphibians that bridged the watery and terrestrial worlds, evolution now gave rise to reptiles, the first true masters of dry land. During the late Paleozoic and early Mesozoic eras, these pioneering reptiles diversified rapidly. Some remained small, agile hunters, while others grew to colossal sizes, dominating their habitats. Dinosaurs, perhaps the most iconic representatives of this era, emerged as both predators and herbivores, filling every ecological niche imaginable. Imagine the first towering sauropods, their necks stretching toward the canopy, while swift theropods hunted in packs, their sharp claws and keen senses honed by millions of years of natural selection. The evolution of vertebrates was not limited to land. Life continued to flourish in the oceans, where marine reptiles like ichthyosaurs and plesiosaurs ruled the waters. Freshwater and coastal ecosystems were bustling with amphibians, early fish and invertebrates creating complex food webs that mirrored the diversity emerging on land. The oceans and continents were now intricately connected, a global stage where every action had ripple effects across ecosystems. Physiological innovations were critical to this success. Vertebrates developed stronger skeletal structures, more efficient respiratory systems, and advanced sensory organs, allowing them to navigate, hunt, and reproduce in diverse environments. The appearance of eggs with protective shells enabled reptiles to reproduce fully on land, freeing them from aquatic dependency and opening up new habitats. During this era, the planet's climate also played a pivotal role. Warm temperatures, high oxygen levels, and vast forests created environments where gigantism and specialization thrived. Seasonal cycles encouraged migrations, breeding patterns, and evolutionary pressures that shaped behaviors and survival strategies. The interplay of environment and biology was intricate, a testament to the power of natural forces working over millions of years. Predation, competition, and symbiosis were driving forces in this biological theater. Large predators regulated herbivore populations, while scavengers and decomposers recycled nutrients, maintaining ecological balance. Social behaviors began to emerge with evidence of parental care, hunting strategies, and possibly even communication among some species, foreshadowing the complexity of future animal interactions. Mass extinctions punctuated this era, each catastrophic event resetting the stage for new evolutionary innovations. The Permian-Triassic extinction, for example, wiped out an enormous number of species, yet life rebounded with renewed vigor, giving rise to the age of dinosaurs. Such events underscore the resilience of life, its ability to adapt, and the delicate interplay between planetary forces and biological evolution. By the Cretaceous period, dinosaurs had diversified into hundreds of species, from the smallest feathered theropods to the largest plant-eating leviathans. Birds began to evolve from small theropods, hinting at the eventual emergence of flight, while mammals, still small and nocturnal, quietly laid the foundations for the next dominant lineage. Ecosystems had reached an extraordinary level of complexity where every organism, from microscopic insects to giant reptiles, played a role in sustaining life's intricate web. This era of vertebrates and dinosaurs is a vivid reminder of life's potential, its adaptability, and the epic scale over which evolution operates. From the first amphibians crawling onto land to the apex predators dominating Mesozoic forests, the story of vertebrates is a tale of survival, innovation, and relentless change. Imagine a world suddenly plunged into chaos. 66 million years ago, a catastrophic event reshaped the Earth forever. A massive asteroid, colliding with what is now the Yucatan Peninsula, unleashed energy beyond comprehension. The skies were filled with dust and soot, blocking sunlight, cooling the planet, and triggering a global ecological crisis. This was the end of the dinosaurs' reign. The Mesozoic era-esque giants were wiped from the land, leaving behind a vacuum in ecosystems that had flourished for over 160 million years. Yet, in this devastation lay an opportunity. Small mammals, previously nocturnal and marginalized, survived the extinction event. Their adaptability, ability to burrow, and varied diets allowed them to endure conditions that proved fatal to the larger, specialized reptiles. In the ashes of a fallen world, mammals began to diversify rapidly, filling ecological niches that had been dominated by dinosaurs. Imagine the first early primates, rodents, and ungulates exploring forests, plains, and rivers, each lineage experimenting with new strategies for survival. Life on Earth became more dynamic than ever. With the disappearance of large predators, herbivorous mammals expanded, feeding on the recovering vegetation. Forests began to regrow, wetlands stabilized, and rivers carved new paths through the rejuvenated landscapes. Predators evolved alongside herbivores, from nimble carnivores stalking prey in dense undergrowth to larger predators patrolling open plains. The stage was set for the rise of highly adaptable, intelligent mammals capable of complex social behavior. This era saw extraordinary evolutionary experimentation. Early whales returned to the seas, evolving from land mammals into marine hunters. Flying mammals, the bats, emerged to exploit the aerial realm, while burrowing species shaped soil and vegetation patterns. Life was no longer constrained by the limitations of the past versatility. Agility and intelligence became key survival traits. Climate and geography played a pivotal role. The continents had drifted into positions similar to modern Earth, creating varied climates from tropical forests to temperate zones and arid plains. These environmental differences fostered rapid speciation, driving mammals to diversify in size, diet, and behavior. Migration patterns emerged, herds moved with the seasons, and social structures became increasingly sophisticated, laying the groundwork for complex interactions that would eventually support primates and ultimately humans. As mammals spread and diversified, the planet's ecosystems became intricately interwoven. Predation, competition, symbiosis, and environmental pressures created an evolutionary crucible, refining adaptations in body size, brain development, and reproductive strategies. The Earth, once dominated by reptiles, was now a mammalian world, dynamic, resilient, and teeming with possibilities for the next chapter of life. This era also highlighted the long-term consequences of extinction. Catastrophic events, though destructive, acted as catalysts for evolutionary innovation, allowing new groups to rise and flourish. Life's resilience is remarkable. Despite mass extinctions, environmental upheavals, and unpredictable disasters, evolution continues, crafting increasingly complex organisms and ecosystems. By the end of this period, mammals had established dominance across the continents. Forests, grasslands, and wetlands were alive with diverse species, from tiny shrews to giant herbivores. Intelligence, adaptability, and social cooperation became central to survival, setting the stage for primates and eventually the emergence of humanity. Imagine a world where forests stretch endlessly across continents, rivers carve their paths through fertile valleys, and mountains rise like ancient guardians. In this lush, dynamic environment, a new lineage began to emerge: primates, our distant ancestors equipped with keen vision, dexterous hands, and a growing capacity for intelligence. Millions of years of evolution shaped these creatures to explore trees, manipulate objects, and communicate in ways that would eventually lay the foundation for human society. Primates were not alone in this journey. They shared their habitats with a diverse array of mammals, birds, and insects, each playing a role in complex food webs. Survival required adaptation. Some learned to swing from branches with agility. Others developed social structures for protection and cooperation. Imagine a troop of early primates watching, learning, and responding to the rhythms of the forest every day, an exercise in survival, innovation, and understanding their environment. The evolutionary stage for humanity was set by a combination of intelligence, environment, and social behavior. Walking upright became a revolutionary adaptation, freeing hands for tool use and enabling more efficient travel across open landscapes. Stone tools, first rudimentary, evolved into more sophisticated implements, reflecting an emerging cognitive ability that separated humans from other primates. Each generation learned from the last, passing knowledge forward in an unbroken chain of discovery. Climate shifts, glacial cycles, and continental movements shaped the habitats of early humans, forcing them to adapt to both extremes of heat and cold. Savannas replaced forests in some regions, leading to new hunting strategies, migration patterns, and social cooperation. Early humans became not just survivors but innovators, using fire for warmth, protection, and cooking, creating shelters from natural materials, and developing early forms of communication that strengthened community bonds. Social structures became increasingly complex. Families and clans formed, teaching the young, defending the group, and sharing resources. This cooperation allowed early humans to thrive in environments where solitary survival would have been impossible. Rituals, early art, and symbolic behavior began to appear, marking the beginnings of culture and the uniquely human ability to reflect, imagine, and create meaning in life. As humans spread across continents, they encountered diverse echoes, from dense jungles to open plains, from towering mountains to arid deserts. Each environment posed unique challenges, driving further innovation and adaptation. Migration patterns, hunting strategies, and the domestication of animals began to transform humans from passive inhabitants into active shapers of their world. By the late Pleistocene, modern humans had emerged, equipped with advanced cognition, complex language, and an unparalleled capacity for collaboration. The dawn of humanity was not merely biological, it was a cultural, intellectual, and spiritual awakening. Humans began to understand their place in the universe, to ask profound questions about origins, existence, and destiny. In this transformative era, every adaptation, every innovation, and every social interaction was a step towards civilization. From the first stone tools to early language, from family groups to nascent communities, humanity had begun its journey setting the stage for agriculture, cities, science, and art. The story of life on Earth had arrived at a new chapter, one where conscious beings could not only survive but also shape their destiny and reflect on the grandeur of the universe itself.